All right, now we are recording. Let me share the screen. I think this is where we left off, correct? So I think we got to here. And now we're going to continue with treatments with artificial preservation. Okay. I think everything's should be working. So one way to prevent wood from, well, let's back up. As you recall, in order for wood to decay, we have to have free water in the cell lumen in order for the decay organisms that secrete enzymes to allow those enzymes to diffuse through the free water and then attack the wood and degrade it. So one way to reduce the equilibrium moisture content in wood is to heat it. So this is a time temperature thing, and there's various schedules for various species. So you don't heat it so much, you don't want to heat it so much that it burns, but you want to burn it a little bit, and you want it to do without oxygen. And what happens then is you degrade the carbohydrates, and one of the things that happens is you can, dehydrate the hydroxyl groups. So when you dehydrate the hydroxyl groups, you can get an ether. And let me see if I can do this. So you can just get, wood has hydroxyl groups. And when you hit it, I'm just going to do this for an arrow. When you heat it, then what can happen is you get this. Okay, so you see what's happening here. You can have the wood can actually cross-link. You get an ether bond. This is an ether bond when you have an oxygen that is this will be the wood is actually going to be a carbon. Right? So there's a carbon here and then a hydroxyl group. So you're going to have wood and then just an oxygen and then more wood. It's actually bonded carbon, oxygen, carbon. It's called an ether bond. And it is hydrophobic and not very susceptible to moisture. And you're going to emit water vapor, right? Because typically these, when you do thermal treatments, you do it above 100 degrees C. So a lot of things happen besides this, but one thing that happens is you reduce the EMC and you make the wood more hydrophobic. You also reduce the strength, you make it more brittle, and you can produce all kinds of other stuff from the extractives. Furfurylaldehydes is one. But it is a way that will prevent.
Excuse me, Dr. Simonson.
Yeah.
Yeah, Kenneth is waiting, I guess. So can you let him in?
I'm sorry, say it again.
Kenneth is waiting, is on the waiting room, I guess.
Oh, so is Dylan. Okay, so these thermal treatments are a way to prevent wood from decaying, and they are effective. Generally, you want to use them in above ground situations or without soil contact, because yes, they resist decay, but it's not as good as loading it up with toxic chemicals, right? So thermal treatments. And here's a picture of one. And I need to somehow get rid of this. How do I get rid of this? Please bear with me. I'm learning lots of new skills here. All right, so this is what it looks like. It just looks like regular wood, maybe a little bit darker. Depends on the species. This has been got started in Europe and it's available in the US. And it's more popular now than it's increasing in popularity. It's more popular in Europe, I think, than it is here. So Europe is generally more environmentally. So you can also have barrier treatments. It's pretty typical when you put a fence post in the ground. If you're doing it for your yard, people don't do this for, you know, if they're fencing 100 acres or something. But in your yard, it's often you can sink the post into concrete. You want to be a little bit careful that you don't create a water trap so that the post rots off. So you need to either leave the bottom open, you need to push it through the concrete, or bring the concrete above ground. So, and you can wrap it in metal. That doesn't work too well, but wrapping it in plastic actually works pretty well. And of course, and this is actually done primarily on utility poles, where they will shrink wrap polyethylene around the bottom part of the pole, the butt of the pole, and bring it above ground. Because remember, your requirements for decay is you need temperature and moisture and pH. And generally the decay zone for wood is the high decay zone, let's say, the high decay zone for wood is about 18 inches above and 18 inches below ground. So there's about 3 feet there. So if you wrap the utility pole in plastic and get the wrap more than 18 inches above ground, you can at least, typically what they do is it doesn't eliminate the need for a preservative, but it will reduce the need for a preservative retention. So you can use a lower retention as less leaching, more environmentally friendly, let's say. And of course, for thousands of years, hundreds of years at least, people have been painting wood to prevent it from decaying outdoors, because if you have a good coat of paint, then your wood is protected, right? And you can also treat it with water repellents. This works to some extent. Generally, the water repellents will not, well, it's what they say, they're repellents, right? So they don't eliminate water. And typically you can get high humidity that can raise the moisture content in the wood higher than we want, higher than the 20%, which is our standard guide. So just from humidity, because humidity will penetrate the water repellents. Also, very difficult to apply water repellents that don't have some kind of pathway through them, some kind of pinhole or something. The same thing is true of paint. That's why you use more than one coat of paint. So water repellents do work. Once again, they don't work great, but they do improve the service life of the wood. So there's, these are various kinds of wraps. So here you see a wrap with metal, and that's, you see it's quite far above ground, and this is a utility pole. Here's another utility pole. And this one is actually called a bandage. So what this one does is, you see that it's the diameter of the bandage is, or the wrap is larger than the diameter of the pole. Inside of this metal casing, there is a, I don't know if it's cotton, but there's fabric, and the fabric is soaked in preservative. And so this preservative will slowly diffuse into the pole over time. Generally what will happen with these generally these wraps are installed on utility poles that are, I suppose it depends on where they're at also and what they're treated with. But they have the utility companies have some guidelines for when they think the pole might be reaching the end of its service life. They will apply one of these wraps. And so they dig a hole around the pole and apply the wrap and then fill the hole back up. And this will extend the service life of the pole, and it's much cheaper than putting in a new pole. Because a utility pole, the expense involved has very little to do with the pole. It has everything to do with the electric wires hanging on the pole and the labor involved in dealing with those. So, plus the liability for utility poles is extremely high. If they fall down, you've got a big problem. So here you can see the testing for decay, right? So this is the favorite of chemists, and is modifying the wood with different chemicals, right? So many different, maybe hundreds of different chemicals have been applied to wood in an attempt to modify it chemically to improve the properties, either fire resistance, decay resistance, or dimensional stability. And probably the most common is acetylation, and this uses an anhydride, acetic anhydride. So this maybe, no, we do, oh, no, where's a pen? No. All right, well, I'll try it this way. So this is acetic acid. And once again, you dehydrate it, and if you dehydrate it, you get this way, because there's a double bond to this oxygen. This is a carboxylic acid. So you have two molecules of acetic acid, and you can form the anhydride. So once again, this oxygen is actually a double bond. Couldn't figure out how to draw a double bond and oxygen up here, so do it this way. So you have a carbon bond, single bond, oxygen, single bond, carbon, and so you have this is acetic anhydride. So when you apply this to wood, and you can apply it as a liquid or a gas, just raise the temperature and this thing will form a gas. And then it will react with the wood hydroxyls, right? And you'll get an ester. So this will turn into, try it again, let's see. So you have, we're going to make an ester, which is So is everybody following this? You see what's going on? There's you have acetic anhydride, and what's going to happen now is the wood. This was originally an OH, so the acetic anhydride is going to react, and what you're going to get is the hydrogen that was on this OH that was on the wood is going to go over here, and you're so you have one molecule of acetic anhydride. It reacts with the wood, and it makes acetylated wood, is what it's called. So you have this acetyl group that is bonded, chemically bonded to the wood. Plus, you also produce a molecule of acetic acid. It smells like vinegar, and you need to get rid of that somehow. So usually they just use heat to drive it off, heat and vacuum to drive it off. So again, yes?
Professor, could you please repeat the explication, the first reaction? I don't know if it was my internet, but I didn't understand the first reaction.
Okay. This is, I'm so used to having a whiteboard. Let me see if I can put it up here. So you have, does anybody know if there's some way I can just draw? This is just like a laser, right?
There should be a pen, Professor.
Yeah, where's the pen?
We can't see that.
Oh,
but
really?
should be one. Yeah.
Oh, I'm not finding a pen. There's a stamp, there's draw. I don't see a pen on the draw. Shoot.
Draw should have a pen, I guess.
Well, there's a wavy line. Maybe that's a pen. Okay. Now. Seen this, right? Oh, that's terrible. So, acetic acid. Ah, sorry. Okay, Maria, can you follow this? I apologize for my scribbles with trying to draw with a mouse. So this is acetic acid, and this is acetic acid. So you have two molecules of acetic acid, and you react them, and basically you just heat them up. You need a little bit of a catalyst, usually an acid or a base, and and what happens is you lose water between them, and you form the anhydride. which is this molecule. This is CH3C double bond O, CO, right? And you can see if you had an OH went to one of these and a hydrogen went to this oxygen, you return back to the 2 molecules of acetic acid, right? So then you have acetic anhydride. Then when acetic anhydride reacts with an alcohol, it will form 1 molecule of an ester, which is this one, plus it will form 1 molecule of acetic acid. So it will revert back to the hydrogen that used to be on the hydroxyl on the wood will move to this oxygen on the anhydride and form the acetic acid back. So you have 1 molecule of ester and 1 molecule of acetic acid from 1 molecule of acetic anhydride. Okay?
Yeah, I understand.
Okay.
Yes. Thank you.
Okay. All right. So acetylated wood is the most common. Excuse me. And actually, acetylated wood is what the wood paneling on the exterior of new PV is. So if you heard Luis's seminar, then he talked about that. The issue with all of these wood modification techniques is they generally require a very high weight gain, whereas with preservatives, you're talking about a few percent, usually less than 5, in order to get protection of the wood. With the wood modification, you need 20 to 30% weight gain in order to get similar protection, which puts you economically non-competitive, right? So acetic anhydride, acetic acid is inexpensive, and so it's the one that's used the most. Like I said, you know, it's commercial right now, and you can buy it right now. Typically, since the 1950s, I've seen acetylation. Well, in the 1950s, I wasn't old enough to pay attention, but since about the 1950s, when the wood modification acetylation was first developed or first commercialized, typically there'll be a company that will sell acetylated wood and it will last for a few years and then go broke, and then 5 or 10 years later, another company will give it a try and they'll last for a little while and then go broke. So maybe now things are different. Maybe now somebody will actually try it and it will work. Clear. And this. Okay. So another thing that you can do is bulk the wood with polyethylene glycol. So if you've ever seen one place where this gets used where it's visible is when people will take a slice out of a trunk of a tree and make a tabletop out of it. They usually have a glass covering on it. I don't know if anybody's ever seen that, but I have. And one of the things that they'll do is they will take the tree trunk while it's still green, before it's been dried, and soak it in a solution of polyethylene glycol. It's usually a molecular weight of 1,000 or 800, somewhere in that range. And it's usually about 15% polyethylene glycol. Everybody calls it PEG, P-E-G. So you soak the wood in PEG, and the polyethylene glycol will actually displace the water. And it's a matter of simple statistics. This is going to be hard to draw. So polyethylene glycol has oxygens in it. So I'm just going to do it like this. So these are oxygens on a polymer chain. And then the wood surface has hydroxyls. So you get hydrogen bonding between the polyethylene glycol and the wood hydroxyls, right? Sorry about that first one. Okay, so, and this should be like this. So this is what happens with water and wood, right? The water is going to hydrogen bond to the hydroxyls on the wood surface. But when polyethylene glycol lays down, in order for the polyethylene glycol to be removed from the surface, you have to release all of these hydrogen bonds at once. And you can have like 100 hydrogen bonds. Once, if the peg lays down flat on the wood surface, you can have 100 hydrogen bonds. So in order for the peg to be removed, you have to release 100 hydrogen bonds at the same time. Probability of that is very small. So the peg can actually displace water in the wood. And then once it does, of course, the peg is very water soluble, but it will bind to the surface. So you can add it as like a 15% solution and the peg will stick to the wood. So this will bulk the wood, so it swells the wood, and it can then prevent decay, but mostly it's used to prevent cracking and checking, right, for the peg. You can do other kinds of polymers in wood, and typically this is done by injecting resins. Like we've talked about treating wood, and you've had the lab on treatment of wood. So instead of blue dye or instead of a preservative, you can, like micronized copper or something, you can inject a polymer monomer like methacrylic acid, and then with a catalyst so that it will polymerize when you heat it up, or you can inject low viscosity glue like phenol formaldehyde, PF. This was done back in the 1950s, and it's a commercial product, or at least it used to be. It's called Impreg or Compreg. Looks like this. You can put dyes in it. And so the methacrylate is also one place where you see that is chopsticks. But also a lot of boat decks are made from wood that's been acrylated. And because it makes it more resistant to salt water and to UV, and you can put UV stabilizers in it and things like that. So the Impreg and the Compreg are dimensionally stabilized. One of the advantages of all of these different wood bulking techniques is that you can get more dimensionally stable wood. And that's also true with the wood modification. And you also get resistance to decay, right? But again, you're looking at very high loading levels, and so very expensive things. So another place where they're used is bow and arrow. The wood, if you have a bow and arrow, and if the bow is made out of wood and the arrow is made out of wood, probably it's got some kind of a treatment. And pool cues, where you shoot billiards, those typically also have some kind of a treatment to give them dimensional stability. All right. And of course, waxes. It's typically you want to prevent moisture, you wax something up. So you can inject wood with waxes. And so you basically have a very high water repellency.
So if you have dry rot or termites or beetles in your wet wood, your wet stumps, and you treat it with PEG, will that kill those organisms?
I don't know that I don't think it'll kill them. It's not like using an alcohol that will dehydrate them. Because typically the peg itself is a solution, but it's very water soluble, and to get this effect of the peg sticking to the wood, you need a higher molecular weight, and the higher molecular weights are more viscous. So it's the diffusion into the wood is going to take a long time. I've never heard of anybody using peg on stumps to try and kill termites. I would be my guess. I've never heard of it or read about it, so my guess is probably it doesn't work.
Okay.
Yeah.
Right. Thank you.
Yeah. So here's another one that is phenol formaldehyde. I think this one is actually infusing wood with phenol formaldehyde, and then infusing, like here you have different plies or lambs, and so that you see how thin they are. So it would be easy to just soak these in phenol formaldehyde resin, and they would diffuse in, or you could put a little pressure on it, but they would treat very easily because they're so thin. And then you can assemble them into a laminated structure, and you're going to have a very good treatment. It's going to have very good mechanical properties, resistance to decay, et cetera, et cetera. So it's going to be nice. And I think you're seeing more of this, and these days, at least people are trying it. I know that Jeff Morrell, one of the professors that used to be here, was involved in some companies that were getting involved in doing this. And then, let me do this. So creosote. Creosote also will bulk the wood, right? You're taking the treatment trick that you're using for creosote is you heat it up, lower the viscosity, put it in the wood. So typically with creosote, you put substantial amounts. Creosote's very cheap. You put substantial amounts of creosote in the wood, and then at ambient temperatures, hopefully, it's not too viscous. And so you can see here a railroad tie. You can see the rail of the railroad tie, rail of the railroad. Here's the tie, and there's the spike. You can see it's decaying. But one of the things I wanted to mention here, because it's an interesting word, is lubricity. So one of the reasons that they use creosote for railroad ties is, in addition to decay prevention, it also lubricates the wood. And if you've ever been at a railroad crossing and watched as the train went by, the rails actually move up and down as the wheels of the train go, as the weight goes on the wheels, right? So the rails are steel, but they actually, if you look at the shape of them as the train goes over them, they're a wave, because where the weight of the wheel pushes down, they'll actually move down. And if you watch the rail, it will go up and down, kind of a sinusoidal motion as the train passes. So it's the spike is like a giant nail, and it goes to the cross tie. And so if the cross tie can move a little bit also, then that's called lubricity when you use creosote. Then that actually gives you a longer service life for the railroad tie.
Is creosote made from coal?
Yeah, coal tar creosote is the most common. You can get creosote from wood too, but the most common is creosote from coal. Coal tar creosote, they call it.
Okay, thanks.
Yeah, it's simply distilled, and it is a really nasty place to work. Okay, so what we want with preservatives is longevity, of course, but we also want marketability. So that means no maintenance, good price, and actually most of the treated wood market is a commodity market, so price is king. And one thing that I always like to remind people of is that really what people make their buying decision on is value, which is the function divided by the cost. So a lower cost gives you a higher value, but higher functionality also gives you a higher value. So if you have something that has better function, like it looks better, it's got a better color, smoother surface, or whatever it might happen to be, that can also give you allow for a higher cost in the marketplace because you have higher value. So other issues, of course, are production efficiency, capital investment. These are things that contribute to the costs. You want those to be as low as possible. However, these days, it requires more of a capital investment than it used to because of environmental considerations. There are thousands of different kinds of organisms, fungi primarily, that will decay wood. So you need some kind of a broad spectrum chemical in order to prevent decay. Now, copper is that, like I said, the most favorable chemical that's used today is based on copper, and it is broad spectrum. It just happens to be not all that toxic to humans or pets, right, or farm animals. You also want it to not bioaccumulate, so don't use DDT, and non-toxic to non-targets. This is stable in the wood, no negative strength effects, low cost, and aesthetic appeal. That is a very challenging list of requirements. And there are basically no products available that do everything on this list. So broad spectrum that is also non-toxic to non-targets has been really difficult to find. And or if you find it, it's not stable in the wood. Or if there's other things that you can do, but you have negative strength effects, like the heat treatment. If you overdo it with the heat treatment, you reduce the strength, right? Or if you could pay 10 times what people pay now for treated wood, there's all kinds of things you could do. But, that's not where we're at.
What's non-toxic to stable mean? To non-target?
Non-toxic to non-targets. So
Yeah, what does
you
that
want
mean?
to be, so you want to typically you want to protect the wood against decay organisms like fungi and termites, right?
Okay.
So you want something, and you've got thousands of different species of fungi, right? But you don't want it to be toxic to
I see.
dogs and cats and birds and squirrels.
Okay, thank you.
Yeah. So the different kinds of preservatives, and we just use blue dye in the treatment lab, but typically there's two different classes of preservatives, oil-borne and waterborne. And there's the big ones, the most common in the marketplace for oil-borne are creosote, pentachlorophenol, and copper naphthenate. Of these, pentachlorophenol is not used so much anymore. It used to be king. It used to be the most commonly used preservative, but it's quite toxic and also contains dioxin. And even though it doesn't contain these particular dioxin that, well, you're all probably too young to remember, or maybe 20 years ago or so, there was a huge outcry about dioxins. And there were, I think it was someplace in Europe, I think in Italy, where there were people that died from dioxin poisoning. And they found dioxins in pentachlorophenol. There's several different kinds of dioxin molecules. But the one that's most toxic, most carcinogenic hasn't been found in penta, but other kinds of dioxins have. And is what people in the industry call pentachlorophenol. People that, researchers that research pentachlorophenol will call it PCP. So you'll find both of those. So pentachlorophenol has really had a lot of trouble and is no longer used very much. Actually, in the old days, so they would pentachlorophenol is oh, this is going to be tough. I'm just going to draw a circle. Too big. So these are chlorines. There's 5 of them. And the aromatic ring with a hydroxyl group on it is phenol. And you have 5 chlorines, so it's pentachlorophenol. Right? Now, if you react this with sodium hydroxide, you can remove this and you'll get the negative charge there, and you'll have sodium. Right. So this is then sodium pentachlorophenate, and it's water soluble because now you've ionized it. So ions give you higher water solubility. And so sodium pentachlorophenate was what people used to use, if you recall the previous lecture, and we talked about short-term protection. So sodium pentachlorophenate in water was used for short-term protection to prevent staining on wood. So they would dip the lumber in it at the sawmill before they would stack it for inventory. And sodium pentachlorophenate is like glyphosate is now. It was the most, so pentachlorophenol, sodium pentachlorophenate was the most ubiquitous pollutant on the planet. North Pole, South Pole, top of Everest, human bodies, dogs, cats, rivers, grass, dirt, everywhere. Everywhere they looked, they found it. The same thing today is true of Roundup or glyphosate. It's everywhere. Mother's breast milk, it's all over the place. So so this sodium pentachlorophenate got banned, and the and pentachlorophenol itself, which is not water soluble, dissolves in oil, also ended up getting highly restricted. And there may still be some places that use it, but to my knowledge, there are not very many. And nobody uses it in any kind of residential application. It's just used for industrial applications, utility poles and things like that. Copper naphthenate is a replacement. Again, we got copper right. This is our favorite wood preserving chemical here, or element. And the naphthenate contributes a little bit, but these are oil-borne and much lower toxicity. Then creosote, we've talked about quite a bit. So then you have another class, which is waterborne chemicals, and the organic arsenicals are copper, chrome, arsenic, CCA, ammoniacal copper arsenate, ACA, ammoniacal copper zinc arsenate, ACCA, and other copper biocides or ammoniacal copper quat and copper azole. So they've all got copper in them. Notice that, right? They've all got copper. The ones with arsenic actually work better. And this one has hexavalent chrome, which is another carcinogen in addition to the arsenic. And it works very well. Also, it works great. CCA is one of the best preservatives people have found, except that it is toxic to non-target organisms. And but it's cheap and it's effective. There are CCA poles that have been in the ground for more than 50 years and they're doing just fine. So just have to get the retention right. So that's in the 1980s, the late 70s and 1980s, people started discovering how toxic these things were, and that people were using treated wood in a lot of different places, including children's playgrounds. So they tested, some people, not the treated wood industry, some other people, scientists, tested the surface of the wood and found that if they just took a cloth and wiped the surface and then tested the cloth, they got arsenic. So then children were being exposed to arsenic on the treated playground equipment. And this, as a result, the CCA, back in those days, CCA and penachlorophenol and creosote were the big three. They had the vast majority of the marketplace, and they all ended up getting restricted status. So you could still use them, but you can't use them for residential applications, only for industrial applications. And you have to have a license to treat with them. And that gave rise to, and these guys were included too, but that gave rise to these other copper biocides, which are less toxic. Borates can be used, but borates have an issue of being highly water soluble, so you can put them in the wood, but they tend to leach out. Now, some people say they've come up with methods that prevent the borates from leaching out, and they are used, the borates are used quite a bit in applications, or venues, I guess we could say, where leaching's not an issue, like indoors, right? So, just to protect from high humidity or to protect from termites. And then micronized copper is probably one of the, as I've mentioned it before, is probably the most common wood treatment today. And again, it's mostly just copper carbonate that's been ground very fine and then treated in water dispersion. And then the copper will diffuse into the wood, because copper carbonate does have some solubility. So the copper will diffuse into the wood and stay there.
So how do they reduce the borate solubility?
You can't. That's the issue. People have tried all different kinds of things. And well, I suppose you can do it, but it's really expensive.
Oh.
So what you want to treat with is borax, because it's really cheap, right?
Yeah.
So about the only thing you can do to reduce borate solubility is to make it an organometallic compound. And now you're talking about lots of money.
Okay.
Yeah. So it's clear. So I mentioned this in the treatment lecture, I believe. I can mention it again. So if you treat Douglas fir with CCA, you can see the level of penetration that you get. And the penetration that you're getting here is from incising. So there have been little slashes have been cut into the wood to try and give some kind of penetration. And you can see that, yeah, you get penetration where they cut a hole in the wood, but that's about it with CCA. But if you use ammonia, ACZA, an ammoniacal-based treatment, you see you get very good penetration. And you still don't penetrate the heartwood, but you can still get good penetration. And the as I mentioned last time, in my opinion, what's going on is the ammonia is deaspirating the pits or dissolving the extractives that are clogging up the pits. So it gives you better flow, better penetration in the wood. And incising looks like this. So you're just cutting slits into the wood. And if you've watched the treatment lab, we had an example of incising because there was a staple in one of the samples and I just left it there to see what would happen. And we definitely got better penetration where we had those staples. So you just run the wood through a set of knives here and cut holes in it. That's called incising. You'll see that a lot in Home Depot with the various species here in the Northwest that are difficult to treat. And it can look, so if you're in a Home Depot, it can look like this. So that's incised wood. Another thing that you can do, go ahead.
Oh yeah, they have green and reddish treated incised wood at Home Depot. This is the green color. What's the difference between the red and the green color?
The green comes from copper. The red comes from, they put an iron dye in there. So it's basically iron oxide.
Oh.
It's just a dye or a pigment. It's a pigment.
All right.
Yeah. So another thing that you can do here, and again, we need to think about basic principles here, is you can kerf the pole. So this gets done sometimes. So you want to treat a utility pole, and you want to treat it well. You want to make it last, and so what you do is you rip it. You put a slice of you rip a slice down the length of the pole, and now what happens is when you get conditions that ordinarily would cause checking and cracking, that kerf will just open and close with humidity, right? Because it's the humidity and swelling and strengthening that'll cause the wood to crack and check and stuff. So kerf will just open and close. So now if you treat it after you kerf it, you have created a shell of treatment, and that shell will protect the wood that is below it. So as long as you have the shell there, then you won't get decay. So that's another technique that's used. So if you have a difficult to treat wood, call it refractory, is see that? Refractory means difficult to treat or impervious. And so if you have refractory species, then this method of giving a shell will oftentimes give you good treatment and good surface life. Environmental issues. So there are spills, there are air emissions, there's leaching, there's all these different things, right? Lots of environmental issues. As I've mentioned, sludge from a wood treating plant was #1 on the hazardous waste list of the EPA when it was first created 50 years ago. And in the old days, scenes like this were common, so they would treat the wood in the cylinder, and I've described bleeding before. So you take the wood out of the cylinder, it's still bleeding, still dripping, And this one looks like it's on a drip pad. So what's required today is you have a concrete pad that has dikes on the side, so no liquid can escape, and then all this liquid will go back to the treatment process. So you treat the wood, it comes out wet, and it drips, and you catch all the drips. Right. In the old days, these went they went on the ground, or they would load. In the old days, people, greedy treaters, in the springtime when they had lots of orders, because everybody, winter's finally gone and everybody wants to start building decks or whatever, they would truck dry the CCA. So they would treat this as CCA with this yellow color. It's water with copper, chrome, and arsenic in it. So they would call it truck dry and kind of chuckle. But what would happen is they'd load the wood wet on the truck and then ship it to Home Depot. And it would be dripping arsenic and chrome and copper on the highway as it drove down the highway. Then people would buy from Home Depot, and Mike Wolcott who's a professor at Washington State, was building a deck one time, got some wood like this, put a nail in it, hit it with a hammer, and got arsenic in his eye. So it was a trip to the doctor. He's okay. He didn't suffer any permanent damage, but that can show you what, in the old days, what people did. So they don't do that anymore. So now it's required that you have dikes all around all of your storage tanks so that nothing can escape, and you have dikes around the cylinder. As I mentioned, you have a drip pad so everything can drip until it's done dripping. Or you put it in a kiln and heat it up, because that will also speed up the process of converting the waterborne chemicals into insoluble chemicals, especially with CCA. The hexavalent chrome will react with the wood and convert to chrome +3. When it does that, the pH goes up. As the pH goes up, you have precipitation of the copper, the chrome, and the arsenic. With the ammoniacal treatments, you bring them out of the cylinder, and as the ammonia evaporates, the chemicals they precipitate and become water insoluble. So most of these treatments, except for micronized copper, have some sort of chemical trick that allows them to convert from soluble form to insoluble form. And you can still get bleeding. This is creosote, bleeding all over the place, and dogs and cats are rubbing up against it. Children are playing around this. So bleeding poles are still an issue, and the treated wood industry is not done dealing with toxicity to non-target organisms. Okay, any questions about what we've covered so far? And if anything comes up, you can also email me and we can communicate that way. All right, I'm going to move on to fire. And this is what you don't want to see. This is from the fire in Paradise, California last year. So just some, this is not really about wood, it's particularly, but just some interesting facts about fire to make people more aware of how dangerous it can be. The U.S. has the worst fire death rate in the industrialized world. So New York City alone has more fires than the whole country of Japan, right? 2 million fires a year are reported in the U.S. So that's a lot. And lots of property damage. Fires kill more Americans than floods, hurricanes, tornadoes, and earthquakes. So, in deadly home fires, 14% had working smoke detectors and alarms. Because you don't hear them, and Smoke detectors fail to operate in 44% of reported fires. I didn't know this. You lose your sense of smell when you're sleeping. And almost 40% of fire victims die in their sleep. So something happens, you get a fire, and let's see if this video will play. Get into it. Okay. Okay. The volume was awful loud on my end. I don't know about you. Sorry about that. So, fire. And here's another video. Let's see what the volume's like on this one.
Professor, we are not able to hear the sound of the video, but we can see.
You can't hear the sound? Nobody can hear the sound?
No, it's not. It's going directly to your speakers. It's not being piped through Zoom.
Okay, well, let's skip this then, and you'll have to watch this. Why not? I don't understand. Okay, so I apologize for my terrible skill set with Zoom.
Don't worry, Professor. I think it's because you have headphones, so you can hear by your yeah.
Was that true on the video before also? Okay, I took the headphones off. Let's see what happens now.
This buoyancy is what gives flames their
Can you hear
familiar
this?
shape. But if you light a flame in 0G, say on the space station, it'll look very different. All the chemical and quantum reactions that make a flame glow can only happen where it meets the air.
Can people hear
So
this?
even though they look like solid cones,
It's a little staticky, but yeah, I can hear it.
as long as there's fuel and oxygen, the flame will burn and burn. Why? It's not the molecular ripping apart that makes a flame hot. It's the formation of new molecules and new bonds is what creates heat. And that heat drives the chain reaction forward, vaporizing more fuel, slamming more molecules into one another, and making the fire burn on. Our species has been gathering around fire for thousands of years, telling stories, asking questions over a flickering flame. And that's part of what helped make us human in the first place. Stay curious.
Okay. Well, I'm going to have to learn how to deal with videos on Zoom because it's not working.
Are we
All right.
doing this in fall term too? Zoom?
God, I hope not. Right now, they are planning to have it to be live fall term. And in fact, I think the last term of summer is going to be also going to be live. But that's just a plan. And the edict has come down that the professors need to be prepared to teach remotely fall term, although we hope we don't have to. So we'll see what happens.
Okay, thanks.
So you have, man, these are, I really like the videos. That's why I use them. I think Zoom, it only really works well if the videos are separate from the PowerPoint and you have to stop the PowerPoint and go to the video and play it and then come back to the PowerPoint is the only way Zoom is set up. But I could be wrong, and I'm going to try to learn more about how it all works. So to start a fire, you need heat input, right? First thing that happens is moisture output. First thing that happens is dehydration. And eventually you get a burning flame. You also get unburnt volatiles. You don't burn the whole thing. And you also have burning charcoal. And eventually it goes to ash. This is for barbecues, but it's, I think it's a nice description here of the 4 different phases. So the first phase, when you're heating things up, you get dehydration. Then you get pyrolysis and gasification. So you start generating carbon oxides, nitrogen oxides, complex organic molecules, right? Hemicellulose will start dehydrating first. Lignin and hemicellulose will start first, and then cellulose will dehydrate. And then they call this phase the burning bush, but this is the phase where you have active flaming going on, right? And then at the end you have char combustion. So here you have the orange glow of the carbon burning, and eventually you go to ash. And down here you can see the temperature ranges for Fahrenheit and Celsius of where these different phases are. So, or stages, right? So if you have, so here they are again. So you have the temperature range and what's going on for the different stages in the wood. When you get to ash, what you've got is typically calcium carbonate, potassium carbonate, and small amounts of all the other things that were in the wood. So one thing you don't want to do is burn treated wood, because most of the time treated wood is going to emit highly toxic gases or particulates. If you burn CCA, you get, which the people did in World War II in Germany, people burned CCA wood, and it emits arsenic particulates, so they got arsenic poisoning, just trying to stay warm. So these are things that you should be somewhat familiar with. And this is a nice picture too of, and Lake Mashinsky found this, and we cannot find the source of, so we can't give a citation to it. But you can see here the steel I-beams draped over the wood beam, the solid wood beam. And that's because the wood chars. So here you can see what happens to the strength loss of the steel and the strength loss of the wood. And this is, oh, this gives you the temperatures here, right? And so you have 25% loss at 30 minutes of fire. I don't know that that's all that helpful. But then this is basically, this is very pertinent to CLT, right? This is one of the reasons that CLT is in mass timber is reasonably resistant to fire, is because it chars, and then the char acts as a barrier to both wood and heat, so oxygen and heat entering to the unburned wood, because the unburned wood is where you would find the source of more fuel for the fire. So the char burns much more slowly, and then you can see the nails here sticking out from this, what used to be a beam. So, so wood can actually be a better material to use in a fire than steel. Fire retardants. So generally, for fire retardants, they are generally a combination of nitrogen, phosphorus, and boron. N is nitrogen, P is phosphorus, B is boron. If you need to remember that, look it up on a periodic table. And these three things together are synergistic. And what they do is they increase the char formation at a lower temperature. And because you get charring, you get reduced production of flammable volatiles. Right? So, and I mentioned this already, the best fire retardants tend to degrade the wood because they're acidic. And that has caused trouble in the past, but things today are pretty calm. The market for fire retardant chemicals is generally governed by regulations, or insurance companies. If in order to get insurance for your building, you need to have a fire retardant treated roof or fire retardant treated interior or posts or whatever, then people will use fire retardants. Otherwise, they will assume that their building will be the one that doesn't burn. And of course, most of the time, they're right. So fire retardants generally are used in more public buildings where insurance companies will require the fire retardants. They're also used in places like some places where some subdivisions might have, they don't call them building codes, but you have the homeowners association will have regulations that all roofing needs to be cedar shake shingles. So then people will, then you want to have treated, fire retardant treated cedar shake shingles on your roof. You don't want your roof catching fire. And so here's an example from the American, this is an old one. It's still called the American Wood Preservers Association in this one. It's now the American Wood Protection Association. But it shows you that the fire retardant formulation is phosphate, boron, phosphorus, boron, and nitrogen. So this is another thing. This is another chemistry speak thing here. So the phosphorus in the wood is not P2O5. They measure the phosphorus as the element phosphorus, and then they convert it to, using molecular weights or atomic weights, they convert it to P2O5 and report it as the weight of P2O5, as if it were P2O5, even though everybody knows it is not. And same thing with boric acid. Boric acid is H3BO3, but that's probably not what's in the wood, but it's reported as H3BO3. So you have to be able to use your freshman chemistry and convert these using atomic weights if you want to find out how you want to make your fire retardant and use the same percentages. Okay.
Is this the same stuff they dump on forest fires? It's orange.
No, I think no, I think those are. I think that's mostly water. I'm not sure what that is. I always thought it was mostly water with the glycol in it to increase the viscosity, so it kind of hugs things and coats them that way.
Okay, thanks.
Okay. It's 11:18. So next we're going to talk about, and I'm a lecture behind. So next we're going to talk about bioenergy and bioproducts. And there's a class that is bioenergy and bioproducts. How many people have taken the class? Let's see. Can you raise your hands or something? Let's see, that doesn't do it. How do I do this? Stop the screen share. Okay. Has anybody taken the class? I forget what the number is. It's a slash class. Has anybody taken it, or is anyone planning to take the bioenergy class?
I have planned.
You plan to take?
Yes.
So my lecture is going to be bioenergy, bioproducts light. And if you want to do a deeper dive, you need to take that class because then you get a full term of bioenergy and bioproducts. And
Is
all
it WSE 573 bioenergy and environmental impact?
Yes. Yes. So it was originally taught, used to be taught by Glenn Lee, but I think now it's being taught by Jerry Presley, our new biodeterioration person. So it's a good class as far as I can tell. I haven't sat in on it myself, but I think it's a good class if you're interested in that sort of thing. I am, obviously, so maybe it's not obvious to you. So we're going to have a lecture, maybe a lecture and a half on bioenergy and bioproducts. I'm actually more interested in bioproducts than bioenergy, but I'll cover it for those people who don't plan to take 573, and that'll be that, and then we'll move on. So I will see you, if I don't see you tomorrow at seminar. It's going to be a good one tomorrow. This fella Bing is really a hot shot. And but I'll see you back here on Thursday. And the lab is posted. It's on YouTube. for the pyrolysis lab. So we will cover pyrolysis Thursday. Hopefully we're going to get to pyrolysis. We should in the lecture, and then we'll actually do a lab. Any questions, comments?
Yes, I do have a question, Professor.
Yes.
So, 2 questions. Our class lectures, are we going to get the recordings posted on Canvas anytime?
The class lectures are all on, they're all on Canvas already. Well, not there, no, the class lectures that we've had are, and also the bioproducts and bioenergy lecture is on Canvas.
I'm not talking about the slides, I'm talking about like the video.
Oh, the videos.
Yeah, the recordings.
You don't have access to them?
No.
If you go to Canvas and Media Space, can you find them there?
Canvas. Where is that again?
Well, they're there for me. And I can't tell if they're there for you or not.
No, all we see is in the media gallery.
Well, what I'm,
You have them in the media gallery.
it takes me time. It takes me time, and I also haven't quite figured out really how to do it, but easily. But what I want to do is get all of the videos on YouTube. So then they're just readily available anytime, anywhere, and no problem. You don't have to log into Zoom or anything like that. So that's my intention, and I'll keep you informed as I make progress on that project.
Okay, sir. Then next question is like, what exactly is the timeline for submission of assignments? Like, we just know it's like Tuesday, Thursdays. Is it before class or at midnight?
Yeah, let's make it before class. So, well, no. If it's due on Tuesday, it's due anytime on Tuesday. It's due before Wednesday.
Okay.
Before I check in on Wednesday, that's when it's due. Right.
Thank you.
Yeah. Anything else? All right then. Everybody have a good day, and I will see you back here on Thursday. Take care.
Thank you, Professor.
Bye-bye.
Thank you.
Thank you, Professor.
Bye-bye.
Thank you.